We're sitting in an early model JK. This Jeep obviously has our CAN interface. You can tell because if I pull back on the shift lever into tap shift mode, we can select which gear we want to be our maximum gear. I'm just going to go back into drive. We got fully integrated cruise control, air conditioning. You can hear the fan. This has got a Camaro SS fan, winding up and slowing down with condenser pressure. This is a 6-liter engine, L96. We've talked about it many times. The L96 engine is still used in the heavy-duty trucks. They're using Gen 5 electronics on the 6-liter engine today. Seems like a lot of guys want to learn the technical side of these engine swaps, so we're going to talk about something else today. We're going to call it speed density versus MAF. Before we get into the speed density and MAF, we have to kind of go back and look at fuel injection from years ago. A couple of things to lay the foundation. One, closed loop versus open loop. Closed loop means you're using an oxygen sensor for feedback to trim the fuel to try to get to stoich. Early fuel injection systems didn't necessarily run closed loop, they ran open loop. Basically they ran what was called alpha N. We're going to talk about alpha N, speed density, and MAF, or mass airflow. The most primitive is alpha N, and basically alpha N does not use load or a MAP sensor. MAP, manifold absolute pressure sensor, senses vacuum inside of the intake manifold. And actually vacuum isn't really the proper word, because in space we all know that that is a pure vacuum. As you go down the atmosphere towards ground level, what you end up getting is the weight of the atmosphere. So I guess we could call it negative pressure, but let's just call it intake manifold vacuum for this discussion. So inside the manifold, as the engine is pumping, because remember an internal combustion engine is really not much more than an air pump, it's creating vacuum in the intake manifold because the throttle valve is closed. By closing the throttle valve, we create vacuum inside of the intake, which also happens to be pumping losses. Pumping losses are when a motor is throttled and it's not running at wide open throttle, which is its most efficient form of operation. So the pistons are going up and down because of the 4-stroke operation in the valves. We are creating vacuum inside the intake manifold. By opening and closing the throttle valve, that affects the intake manifold vacuum. Obviously at wide open throttle with the valve all the way open, the intake is going to be basically open to the atmosphere. We're going to talk in kilopascals when it comes to intake manifold vacuum, because I think it's the easiest thing to comprehend. 100 kilopascals is basically sea level atmosphere. As you go up, it'll drop down a little bit. So here in Vegas, we're at like 95, I think, kPa. When the engine is running under full vacuum, you're probably going to be running about 20 to 30 kPa. So when the throttle valve is closed and you're idling, the intake manifold is under a pretty high vacuum. Let's say 17 inches or 30-ish kPa. As you open the throttle up, the vacuum's going to drop. Alpha N essentially looks at the throttle opening, how far the throttle valve is open, and engine RPM, and bases its fuel strategy on that. There is no feedback from an oxygen sensor, there is no load from a MAP sensor, and there is no airflow calculation from a MAF, or mass airflow sensor. Basically it's just looking at engine RPM and throttle valve position, and it can get a pretty crude approximation of how much fuel is required. In the early days of fuel injection, we did not have the precision that we have today. By adding an oxygen sensor, we now have a feedback sensor that we can base fuel strategy on. Now alpha N is going to work really good for a race vehicle where it's wide open throttle. You don't really care too much about part throttle operation or drivability. It's simple, it's reliable, and it works good on the track. But obviously that's not going to work well on the street because we have emissions and drivability to be concerned about. One step up from alpha N is speed density. Speed density adds a MAP sensor, manifold absolute pressure sensor. This indicates load. So by adding load into the equation, we can much better deliver the fuel and spark in most cases. Now speed density can be both closed loop feedback, running O2 sensors, or not. A lot of the racers like to run speed density without an O2 sensor or a wideband O2 sensor. And I guess a little explanation of O2 sensors would be in order here. Narrowband sensors can really only target one point, and that's stoichiometric. That's 1.5% oxygen in the exhaust stream. A wideband O2 sensor is usually powered, usually 0 to 5 volts, and it can indicate a wide range of air-fuel ratio. Let's say from 8:9 to 1 all the way up to 17:18 to 1. 17:18 to 1 being very lean, 8:9 to 1 being very rich. Now most race engines are going to run in the 10 to 12 to 1 ratio. So with a wideband, they can actually tune the engine to the mixture that they want using that oxygen sensor. So in a race engine, speed density will indicate load. You have RPM. It's a pretty good setup. Now manufacturers have used speed density and use speed density quite often today. In fact, Wrangler JKs and now the JL are speed density operated with a closed loop feedback. They have an oxygen sensor feedback along with speed density, and they are not running a mass airflow sensor. Speed density can work really well, especially if you're staying at one altitude. Now, if I were to drive from where I'm at right now, which is about 2,200 feet, and go up to the top of that mountain, which is over 8,000 feet, all in the same ignition cycle, that can be challenging for speed density, because remember, speed density is basically sensing vacuum and basing fuel strategy on engine load as accurate as that vacuum can indicate. But if I go from sea level to 8,000 feet, let's say, the atmospheric pressure changes quite dramatically. So in the early days of speed density, manufacturers would actually recommend that you stop about every 4,000 feet of altitude, whether you're going up or down, key off, and then key back up. And the main reason is the MAP sensor, the manifold absolute pressure sensor, can not only act as the engine load sensor, but also as a barometer. So when you key up, it takes a reading of what atmospheric pressure is at whatever altitude you're at. So if you drive around the streets at the same altitude, speed density can actually work pretty good. But if you change altitude dramatically, that can throw off the MAP sensor. So you want to reset that as you go up in altitude or down in altitude. I know some of the JKs, especially the Penstars, could get sensitive, especially if you were to go up to, let's say, 12,000 feet from 4,000 feet. Your engine might start stumbling, running lean. You had to cycle the ignition to get it to run proper again. Back in the 90s and even the 80s, two MAP sensors were installed. One open to the atmosphere, one to intake manifold vacuum. By doing that, now we have a more accurate measurement of what atmospheric pressure is. And a lot of these 6-liter motors, like the one I'm driving right now, actually did that. Adding closed-loop feedback or oxygen sensors to speed density can be very precise. And that's basically how most of the Chrysler, or at least the Jeep Wranglers, operate. You are running in a speed density mode without a mass airflow sensor. You're running off of RPM and intake manifold vacuum, and then we're dependent on the oxygen sensor for feedback to trim the fuel. So that works pretty good. Now, is it as precise as a mass airflow system? No, not in my opinion. So in a production vehicle like a Wrangler JK, you have all these different sensors: air intake temp sensor, coolant temp sensor, and basically what's missing is airflow. We don't know how much air is going into the engine. Airflow can vary greatly based on atmospheric pressure, humidity, temperature. So having a MAF sensor can really be a benefit. However, the MAF sensor can also be problematic, and by eliminating the mass airflow sensor, we end up having to replace the actual airflow data with calculated airflow. Chrysler knows through research and tuning and testing approximately what the airflow is going to be when we look at the intake manifold vacuum and all these other temperatures and the engine RPM, and then they can calculate using a lookup table what the airflow is. It's called calculated airflow, and it works good enough. One thing Chrysler has really been heavily reliant on is torque management, and a lot of the manufacturers are going to torque management based operating systems now. In fact, GM is doing the same thing with the 8-speed transmissions and the LTs. And essentially what we're looking for is load, and the transmission bases its shifting strategy on load. A lot of you guys with superchargers are finding out that when you take a 1-bar operating system, 1 bar meaning normally aspirated, 2 bar meaning forced induction, whether that's supercharger or turbocharger, because the operating system has to know when you cross that threshold from being normally aspirated to boost. And if it doesn't know that, all sorts of weird things can happen. Now, since we're basing our shifting strategy off of intake manifold vacuum as being one of the primary sensor feedbacks, the transmission is reacting to what it feels the engine load is. Now, if we take a 1-bar system and then put 2 bars into it, let's say we're running 14 pounds of boost, the transmission can get very confused. And this is one of the challenges running a supercharger on a V6 speed density system. With speed density, we do not have actual airflow calculations. We don't know precisely how much air is going into the engine because we don't have anything to sense that. What we are using is engine load, and the supercharger modifies the intake manifold vacuum because it's taking it from a normally aspirated state to a boosted state, and hence you can get unwanted drivability, surges, hesitations, flat spot, cruise control hunting, etc. Now, if the operating system is properly set up for 2-bar, 3-bar, then it can handle that. If we look at factory operating systems like the LSA or the LS9 or the LT4, GM has taken into account the 2-bar operating system, and in some cases 3-bar, so that as it crosses that threshold from normally aspirated into boost, the operating system knows what the torque management is. So if you're running a 1-bar speed density system, even if it's closed loop, there's challenges if you try to modify that with any kind of forced induction. So now let's talk about the most sophisticated of the operating systems we're discussing, and that's going to be the mass airflow based operating system. I am a big proponent of mass airflow systems on the street. I don't think they have any place on the track, but on the street, mass airflow sensors in operating systems can lead to better drivability, better economy, and better emissions, in my opinion. Now, does that mean it's significantly better than a speed density system? Probably not. Speed density can be very accurate using closed loop feedback. However, I do believe the mass airflow system does have some advantages. With speed density, we're adding a MAP sensor or a manifold pressure sensor, which can give us demand and load and much more accurately control fuel. Going into the mass airflow system gets much more complex because now we're adding a sensor that can actually detect how much air is going into the engine. And as discussed, this can be very beneficial because if you change altitude, temperature, humidity, the density of the air can change, and a mass airflow sensor can better sense that than speed density or alpha. Manufacturers have been using some form of air meter for a long time. I remember the early Bosch setups that had the toilet bowls, I call them, which had basically a plunger that moved up and down based on airflow, and that would change the metering of the fuel. I remember early on the Nissans had a flapper type airflow meter. Actually, several of the manufacturers did. Mitsubishi, a lot of the Asian manufacturers use that setup. I remember taking them apart back in the 80s and 90s, and they had spring-loaded valves that would move based on the amount of incoming air. And these springs would get weak over time, so they'd have a sprocket. You take a screw out, rotate the sprocket to increase the spring tension, and then it would work again. And they were mechanical and a little bit troublesome, but it was their attempt at measuring airflow into the engine. Before we actually talk about how the mass airflow system works, we should probably talk about the benefits. Back in the 80s, Corvette MAF systems, tune port, that included the Camaros and the Trans Ams. They ran a MAF sensor, MAF sensor, and they ran awesome. I remember getting 20 plus miles to the gallon in these MAF Corvettes. I actually had a 1984, 1985, I don't remember which. No, it wasn't an 84 because they had the twin tune port. But I was getting 20 plus miles to the gallon. Throttle response was instant. When they went to the speed density system later on, it just lost something. That throttle response wasn't there. It just wasn't, the drivability wasn't as smooth in my opinion. They did have problems in the early day of the MAFs because most of the current MAF sensors use a hot wire. In a hot wire MAF, the way it works is they put a current into a wire to heat it up, and they try to keep that wire at a constant temperature. The more air that travels over that wire, the more the wire cools down, so the more current is required to heat the wire back up. By looking at the amount of current required, we can determine how much airflow is going into the engine. Modern MAF sensors mostly work off a frequency. They don't put out an analog signal. They put out a hertz or a frequency. On a standard GM system, 2,000 to 3,000 hertz is idle, and you can go up to 5, 6, 7, 8, even 10,000 with high airflow rates. But in the early days of the hot wire MAF, it was troublesome. The MAF would get dirty, so what GM did was they came up with the burn-off system. And the MAF burn-off system was very troublesome. What would happen is after you shut the vehicle off, the operating system would heat up the wire red hot that would potentially burn all the contaminants off the wire. So the next time you started the vehicle, it was clean. If the wire were to get contaminated, that would skew the airflow measurement. And that is a problem today, especially in an off-road environment, because if you're not running a good air filter, and my customers as well as many other Jeepers have found out that if you don't run a good air filter with a MAF system, that wire can get contaminated with dirt and dust. And for the most part, you're not going to have a problem driving around in the street, running trails. But if you're running in a wagon train at Johnson Valley where the dirt is like silt, it's very fine, it goes through the average air filter because they can't handle the micron level, and that gets onto the MAF sensor. Eventually it's going to pile up and skew the airflow meter readings, and then you're going to start feeling a bog or a hesitation. So MAF sensor cleaners became popular, where manufacturers would actually recommend checking the MAF if you had a problem and then cleaning it. You don't want to use brake cleaner, you don't want to use carburetor cleaner, because that can damage your MAF sensor. There are specific MAF sensor cleaners out there that you can use for the purpose. But early on they used these MAF burn-off relays, and these were troublesome, getting enough energy to get the wire red hot. I remember the MAF burn-off relays and the fuses blowing. They were troublesome on the IROCs and Camaros at the time, but they worked great when they worked. I was really a big fan of the MAF sensor. What the MAF sensor can offer is better drivability on the street, in my opinion, because now we're not using lookup tables to figure out what airflow is. We're actually using actual airflow, and that way the operating system can more effectively deliver fuel and spark. I find that operating systems using the MAF sensor can be smoother. The transitions, getting on and off the throttle, shifting, because using the actual airflow value, I think, helps. A speed density system running an O2 feedback is very accurate, because we're actually using an O2 sensor to determine the actual air-fuel mixture. But I feel that the MAF sensor using actual airflow can actually refine it beyond that. You get smoother throttle response, in my opinion. Transitions from off-idle to cruise to wide-open throttle, I feel, are smoother. Now, guys on the track or race car guys, they don't want to mess around with the MAF. They just want to run speed density. When a MAF is working properly, I don't think anything can match it. The Gen 3 motors and the Gen 4 motors run a MAF sensor, and the air intake temp sensor is usually built into it, because air intake temp sensor is critical for the operating system to know for the incoming air, which is primary air into the engine. That, combined with the airflow readings, means accurate fuel delivery. If you're turbocharged or supercharged, they can also add more intake temp sensors to differentiate between intercooler temperature and ambient and intake. What it's all about is the more data you have, the more accurate the fuel delivery can be. These MAF sensors are working really fast these days. There is no delay in these things, they're instant. So going from the old mechanical airflow meters to the modern MAF sensor has really made the drivability of these vehicles a step up, in my opinion. If I'm going to go from 2,000 feet where I'm at now to 8,000 feet where I'm going in one ignition cycle, this MAF sensor is going to read the air density and the airflow better than a speed density system, which really only had a barrel reading when you turned on the key, and then it basically has to use lookup tables after that. So a sudden change in altitude or a dramatic change in altitude can affect the way this vehicle runs on the same ignition cycle. The Gen 5 motors have even taken it a step further. They've added a humidity meter, because the moisture in the air obviously has an effect on the density. So now we're looking at air temperature, humidity, and airflow. And the more information the computer has, the better job it can do. So in my opinion, having actual airflow calculations in the operating system is an advantage. Running speed density like the Chrysler operating system does works very well. However, I do believe it has limitations, especially when you're restricted to a one-bar operating system and you want to go with forced induction like a supercharger or a turbocharger, because now, being torque management based and using your barrel sensor as one of the primary feedback sensors can really confuse the operating system. You can take a Gen 3, Gen 4 LS engine and turn the MAF sensor off so the operating system does not look at it, and you can run speed density. And a lot of guys do that, especially if you're on the track. The downside to the MAF sensor is they're extremely sensitive. Even slight things can throw them off. And once your mass airflow sensor gets out of whack, whether it's the sensor's going bad or it's contaminated or you have an air leak, then it can be hard to chase down what the problem is. A plugged air filter, an air leak on the throttle body side of the MAF can cause dramatic changes in fuel trim changes in the operating system. Something that probably would not happen with a speed density system because it's just using up the lookup tables and it's ignoring that airflow that's coming through the intake. The design of the air intake, the restriction of the air filter, a lot of things come into play when you have a MAF sensor. And if it's not exactly right, that MAF sensor or that MAF system is not going to work the way it was intended. We're working in California, and when you work with an executive order intake, these intakes are flow tested to make sure that the characteristics work with the MAF sensor. You can't just take a MAF sensor system, build any intake you want, throw the MAF sensor on and expect it to work properly. If you add a snorkel or change the intake up, the odds are the MAF calibration is going to have to be changed. And that's not a hard thing to do these days because most of the tuners have the ability to change MAF calibration. What that means is you can go into the operating system, and the Gen 4 and Gen 5 engines are coefficient-based systems, which basically means the fuel tables are no longer block-learned tables. It's not blocks with values in it like the old alpha systems. There's coefficients that are multiplied on the fly to come up with your fuel strategy, and there's a lot of these coefficients: air intake temp, MAP sensor, MAF sensor, and O2 sensor feedback. So there's open loop modes, there's closed loop modes, there's a lot of different factors that go into the final fuel delivery. One of them is the MAF sensor feedback. So if you were to have a very restrictive intake on it, let's say you added a snorkel to a MAF system, the restriction in that air intake is going to be different than if you just had a 4-inch pipe that was about 1.5 feet long. The MAF sensor likes to run in a straight section of tube. I believe GM wants at least 3 to 4 inches on either side of the MAF sensor for straight airflow to get an accurate reading. So when the virtual fuel table is right, your long-term fuel trims are going to be close to zero. Fuel trims are going to be another discussion because they are a very important subject. But the bottom line is, if you look at your long-term fuel trims, that's basically the culmination of all these coefficients working properly. And if you're running near zero, what that means is the operating system is programmed appropriately for that application. If you're running plus 20%, minus 20%, essentially that means that the computer is pulling 20% fuel or adding 20% fuel based on the oxygen sensor feedback to keep the vehicle at stoichiometric. So by looking at these long-term fuel trims, you can tell if your MAF sensor, assuming everything else is in order, if the MAF sensor is calibrated properly. So the frequency the MAF sensor puts out and sends back to the ECM can be changed. You can tell it, at this airflow the frequency is this value. At that airflow the frequency is that value. And if you do that properly and keep the MAF sensor close to where it needs to be, then the system just runs awesome. The O2 switch rapidly. The amplitude and the frequency of the O2 sensor switching is very critical, not only for catalytic converter operation, but just for the best overall economy and drivability. If you were way out, let's say you were 15-20% out, and the computer was fighting that, then you might see that those O2 sensors are skewed. We do have an average O2 sensor feedback value, as discussed in the previous video, 0.450 volts. That's 450 millivolts is stoichiometric. So in an ideal world, we want to see the average O2 sensor feedback at 0.450 volts because we're switching above and below it. But that's just not going to happen because we have alcohol in our fuel, we have all sorts of environmental changes, we're changing altitude, we're changing temperatures. So the long-term fuel trims have to handle that. But the bottom line is you want to see those trims stay as close to zero as you can. Obviously, if I'm going to go from where I'm at up to the top of that mountain, I'm going to change several thousand feet in elevation. A barrel system is not going to deal with that as well. Yes, it can look at the O2 sensor feedback. Yes, it can look at the intake manifold load or vacuum, which will decrease because as you go up in altitude, there's less density of air. Remember, open space is a pure vacuum. Our atmosphere has weight to it. So the lower you go in the atmosphere, the more weight there is in the air, or air density. So as you go up in altitude, that air density decreases. There's less weight. So the engine has a harder time breathing. The map sensor will pick that up, but if you combine the map sensor feedback with the O2 sensor feedback, then actual airflow, it can handle the altitude changes much better. From 2007 all the way through 17, even 18, with the Wrangler JK and now the JL, Chrysler has chosen not to run actual airflow. They're running speed density. And for the most part, it works great. If you were to have a stock Pentastar or a stock 3.8, and you do not modify the intake, you do not put a supercharger on it, you do not put a turbocharger on it, the results are actually very good. Now, Chrysler tuning has always been more difficult than GM tuning, so it's not quite as easy to tune a Chrysler engine as it would be an LT or an LS. So what it comes down to is, since you're not running a MAF sensor in your JK or your JL, you have to live with speed density, and it works just fine. If you do add a supercharger or a turbocharger, just expect to spend time on tuning and getting things dialed in properly. I do not believe the results will ever be as good as a pure, normally aspirated engine in speed density, but a lot of progress has been made in that area. The MAF sensor can get contaminated not only by dirt, but by oil. So if you were to run an oiled air filter and you over oil it, or even if you don't over oil it, there's instances where the MAF sensor can get contaminated and go out of range. You're going to start throwing some codes, and I'm going to throw a couple of codes out there because these are pretty common. P0101 and P0102 are the most common. Let's talk about P0102 first, because P0102 is circuit failure. Circuit failure basically means that there's a circuit failure. You have power, you have ground, you have sensor feedback. So it's pretty simple usually to check power, ground, the sensor itself, make sure it's putting the frequency out. That code is usually pretty easily diagnosed. P0101 is MAF irrationality, and let's talk about that because the MAF sensor has advantages by adding airflow calculations to the operating system, but if that airflow calculation is not accurate, then it can be a headache. And what happens is the computer compares the airflow that it sees from the MAF sensor to the other parameters like engine RPM, throttle position, and intake manifold vacuum. And if it doesn't make sense, if the airflow coming into the engine does not match what the computer thinks it should be, then you're going to throw P0101. So it may not be out of range all the time. It may be you're driving around town and you have no issues, then you get on the highway and you throw a 101. You'll usually see this accompanied by the long-term fuel trims creeping up or down. They'll usually creep up or down 25 to 30% before you throw the P0101. And that's kind of critical because you want to monitor what's going on when this happens. If you throw a P0101 MAF irrationality, there's a very good chance you're going to revert back into the speed density mode. So the computer is saying, this doesn't make sense, the airflow coming into the engine does not match all these other feedback sensors, so we're not going to rely on actual airflow anymore, and it ignores the MAF sensor and then goes back to a predetermined lookup table. So you're running speed density just like you would be in a Chrysler operating system. It's a limp mode and it can get you home. You can literally pull the intake off of a MAF system. It'll take a couple of key cycles, usually the engine will die, but eventually it'll kick into speed density and the engine will run. Now it won't run great, but it'll run good enough to get you home, drive around, whatever. So now the problem comes, what is causing this MAF irrationality? Well, we already talked about a couple of the issues. One could be the MAF is contaminated. You have dirt on it, you have oil on it, clean it. You could have a bad MAF sensor. And I'm going to throw this in, use an AC Delco MAF sensor. Do not use one made in China or a budget MAF sensor. These MAF sensors are extremely precision devices, and we have found that cheap MAF sensors, they do not work well, they are not accurate, and they will cause you nothing but headaches. Spend the extra $20 and get an OE Delco MAF sensor, and that will solve a lot of your issues. Air intake leak. Now when I say air intake leak, that does not just have to be in the air intake itself. Obviously the air filter to the air intake tube, and the air intake tube to the throttle body, but also the scavenge tube. That's the tube that comes off the engine that is fresh air for the positive crankcase or PCV system. Basically the PCV is scavenging the crankcase by pulling air in through a PCV valve. Well, that air has to come from somewhere, and it comes in through that scavenge tube, which is pulled in from the intake. Now note that that tube is between the MAF sensor and the throttle body. By doing it that way, the MAF sensor can actually calculate or use the amount of air being pulled in by the PCV in its airflow calculations. If that tube were to be put in on the other side of the MAF sensor, on the air filter side, then it would not take that into its airflow calculation and could be more inaccurate. And I have noticed that guys will put tubes in backwards and or just put that scavenge tube wherever, and it does not work properly. You want that to be read by the MAF sensor. The oil filler cap, the dipstick tube for the engine, all of these can leak air into the crankcase. The intake manifold gaskets, the power brake booster, the PCV valve, the purge valve, all of these can leak air and get sucked into the crankcase and cause the MAF sensor to read inaccurately. The mass airflow sensor is extremely sensitive and can measure the smallest changes in airflow. So the smallest things can cause the MAF sensor to go out of range. Proper fuel pressure and the proper gasoline is also required for your engine to run properly. If you were to drop down to 55, 50 psi because you have a weak fuel pump or a plug filter, that's going to lean the motor out. Now the MAF sensor is going to pick that up and you're going to see the fuel trims increase. You do not have a problem with the airflow meter or the MAF sensor, but the MAF sensor is a symptom of a cause, which is low fuel pressure. Same thing with gasoline. If you were to put a gasoline in with high alcohol content, let's say 15, 20, 30%, the operating system is going to pick that up. You're going to see the fuel trims react. So the MAF sensor, again, is not at fault. The MAF sensor is doing its job. It's reading the airflow, but the fuel trims are going out of range. So in conclusion, running with an airflow meter can have an advantage over running speed density without an airflow meter if properly set up and maintained. If not properly set up and maintained, the MAF sensor can be a disadvantage.